Hey, I'm Michael.
Hi, my name is Colin.
Hi, my name is Ben.
Hi, my name is Sam.
Hi, my name is Madison.
Hi, my name is Grace.
Hi, my name is Dave.
Hi, my name is Eli.
Hi, my name is Mackenzie.
Hi, my name is Ty.
Hi, my name is Aaron.
And we are ICEBERG ASV.
Our team is made up of 13 people from a variety of disciplines, such as engineering students, commerce, and we even have students from the Marine Institute. No one has set roles. We have a very flat dynamic structure. So although there are primary focus groups such as electrical, design, marketing, or software, we allow people to explore outside of their own discipline or their interests so everyone can grow and learn as much as possible.
We decided to name our team ICEBERG ASV because we felt that the iceberg is a really nice metaphor for our design team, because people on the outside only see the final product, see the boat that we made, but which is much like the tip of the iceberg. But in reality, like, most of the iceberg is underwater that no one ever sees, and that's similar with this design project. Like, there is so much that goes on behind the scenes, and people are working multiple days a week, going through lots of headaches and struggles and lots of successes as well. And I felt that that was kind of homage to the people on the team and all the work they put in to make our boat possible.
ICEBERG ASV really started when Madison and Michael and I all got together and we just wanted to do a project together. We were all friends, we were all really interested in engineering, and we were looking for a challenge. So when we came across the RoboBoat competition, it immediately felt right. So our strategy was to learn by doing. So a lot of our work was in iterations. We started really small, so we built a really small RC boat and drove around a swimming pool. That was kind of ground one, and we just started to build upon that. So our next iteration, we would bring in more technology, and we just continued to iterate on our designs until we arrived at our final product.
Yeah, so when we were structuring ICEBERG ASV, really the idea was that we just get a bunch of smart people in a room and try to build something cool. So because of that, we look at it like everybody is not really a specific discipline or they're doing a specific thing. We're all just engineers, we're all smart people, and everybody has a say at the table.
And I think that mentality really helped us learn exactly what was going into each design and how we could improve bit by bit.
The three tasks that ICEBERG is selected to focus on for the 2023 RoboBoat competition are the Panama Canal, Magellan's Route, and the Northern Passage. These tasks were selected because they're the simplest tasks for our beginner team to focus on, as well as these three tasks are a staple for the RoboBoat competition and are consistently used each year.
Because this was our first time going to the RoboBoat competition, we decided to go with a design that was simple yet robust. That's why we decided to do a catamaran design for our hull. So this means we had two hulls. We chose this because of its stability and its ease of use. It is also great because the dual hulls can be modular for getting our boat to and from the competition. So we connected our hulls with a bridge, and that bridge can deconnect from each of our hulls and fit easily into our delivery box. We developed these hulls through an iterative design process through several buoyancy tests. Our hulls are made of foam, so they are extremely buoyant, so we had to work on weight distribution and whatnot across the hulls. Another thing we did with our iterative process was develop our thruster mounts. So to begin, we had very small, simple thrusters on our first design of the boat, and then we started using the Blue Robotics T200 thrusters. So obviously that was a huge increase in thrust, and we had to account for that in our thruster mount designs. So we went through several iterations of our thruster mounts, one of which just completely failed and the thrusters fell off. We had to account for the vibrations. So yeah, that failure has led us to where we are now with our thruster mounts.
One of the design requirements for the 2023 RoboBoat competition is a kill switch for your ASV. Not only did we decide to do this for the design requirement, but also to protect our components on our ASV. Our kill switch consists of two different systems, a physical kill switch and a remote kill switch. In order to align with our design strategy of keeping it as simple as possible, we sourced our physical kill switch from an industrial supply store. The kill switch we selected already fit the design requirements for the competition. Therefore, we could easily integrate this into our thruster circuit. For the remote kill switch, we decided to design this on our own, using parts and design strategies that we've already learned and are familiar with. This includes using Arduinos that a lot of our engineering team is familiar with, as well as a relay circuit that we bought in an industrial supply store.
The Hollybro Pixhawk 6C was the model chosen for our flight controller as an economical choice that's able to perform all the tasks required by the boat. The flight controller is a very important part of the electrical system as it is the central component for the rest of the connections. It provides connections and communications with various components such as the GPS, the batteries, and the TX2 computer, and allowing the rest of the circuit to branch out from there. Along with the physical on-boat connections, the Pixhawk provides a wireless connection to land through the use of telemetry radios. This allows the team to monitor battery life, GPS coordinates, and much more using the Q Ground Control Mission Planner software. This transition was made easier through the ability to monitor controls sent to the motors in Q Ground Control.
The challenge that our software team is going to complete this year involves moving from point A to point B based on the locations of navigation markers within the course. To identify what each type of navigation marker is and the relative positions to our ASV, we're using an Intel depth camera and a LiDAR. Also, to keep track of the position of our ASV within the course, we have a GPS and IMU. To implement this in software, we're using the ROS navigation stack, which has a lot of resources online, so it makes it relatively easy to implement for a software team that's trying to overcome the steep learning curve of learning ROS. For testing, we're using the Gazebo simulator, which has a physics engine and plugins for each of our sensors and the dynamics of driving a boat through water. This makes it easy to quickly test small software changes instead of having to go to an actual testing tank every time and make a change. The software generates goal positions based on where the navigation aids are. In other words, it plans a path through the course.